All right, we're back. In our last video, we got introduced to linear search. Well, really, we had done linear search before. We got introduced to time complexities, asymptotic runtimes, big O notations. I kind of use those words interchangeably. But today we're going to build upon that by getting introduced to binary search. This one we will end up coding because it is more complex. Let's get started. Compared to the asymptotic runtimes of sorting algorithms, linear search is quite efficient. So I told you in the previous video that we have sorting algorithms that operate in n squared. In the worst case, that's what this big O means, keep in mind. In the worst case, they would do n squared comparisons. Some of the best sorting algorithms we have are somewhere in here. They can do n log n, as we come to call it, and reduce this a little bit. This is linear logarithmic, by the way. Linear search, as we saw in our last video, is here. Right, so this is a scale. Like constant is the best you can do. We saw that some of our searching cases actually ended up in best case scenario, right? And with linear search, if the element you are searching for is the first element, you can enter a constant scenario. But having a constant scenario as the worst case is pretty rare. Linear search is somewhere in here, right, in the worst case. And we care an awful lot about the worst case because the worst case is what is going to cause someone to leave your website if it is taking forever in order to perform the algorithm, for instance. Sorting algorithms are in here, in this realm. So what I am saying is that searching is a lot more efficient than sorting. And I think a lot of people would just innately get to that without even seeing a sorting algorithm. However, we can do even better than this, provided that the data is in order. Okay, so this video is going to explain binary search. I highly recommend that you pause my video and watch this one. I will put a link in the comments, but as you can see, there is a little bit in the slides, but you don't have to. We're going to learn about it right now. Binary search works by continuously breaking the array into halves and checking a midpoint until the key is found. A precondition exists that the array must already be sorted, right? So that is the big thing about binary search. Your stuff has to be in order, but if it is, we can find it super fast, okay? So let's consider an array of integers. I'm going to break this array in half. Now, in practice, as you're going to see, we don't actually break the array in half. All we do is kind of lower our search parameters. So you see there's these indices, right? I have these markers that are going to be indexes that mark, kind of the search area. Right now, this is saying that everything will be in the search area, everything in the array. We do this because managing these two integers, these two indices, is less processing power. It's a lot more efficient than actually breaking the array in half. For us to break the array in half, we're literally talking about creating a new array with like half the length, transferring elements over, right? That is a very taxing thing compared to managing these indices. So we're going to simulate breaking the array in half by really just lowering our search parameters. Right now, everything is a consideration. So let's say that I want to search for the number 6 inside of this array. You and I can clearly see it's right here, but our algorithm has to basically process it. It's got to go through the array until it finds it. So what this is saying is the first thing we want to do is find the midpoint, the element that's in the center. Okay, right now we got 1, 2, 3, 4, 5, 6, 9 elements. That means this midpoint is slap dab in the middle at 14. Okay, we're going to ask the question. Is the number that I'm looking for 6 less than, greater than, or equal to my current midpoint element, which is 14, right? Because this is an order, that's super important. I'm going to ask, is it less than, greater than, or equal to? In this case, 6 is less than my 14. So what that tells me is that I can ignore this right-hand side. 6 isn't going to be over here. It's going to be somewhere over here on the left-hand side. So we are going to break the array in half by just limiting our search parameters. I'm going to bring end down. I've already considered 14. So what I want is for 10 to be basically the stopping point. We'll make end mid -1. So is the key 6 less than, greater than, or equal to our element at mid? It is less than. So because key is less than elements at mid, we need to lower the search area by bringing end down. Elements is my array, mid is the current index. Okay, keep in mind mid is an index. So we'll bring end down to here. So what this means is I am going to now consider this left-hand side. Notice that I'm not breaking the array in half. I'm just lowering my search area. Now what we're going to do is find the midpoint. In this particular case, there's two possibilities. Our algorithm, depending on how we write it, is naturally either going to favor the left or the right. And it will always favor the left or the right from that point on. Okay, your algorithm can choose either. It doesn't matter. We'll look at the differences in code. In practice, your algorithm will favor one side, left or right, over the other. And we'll say that we favor the left side. And once we start favoring the left side, we'll always favor the left side. We're talking about like it's a -1 type of thing. So now that I have a new midpoint decided, right? I'm saying I favored, out of these two, I'm going to favor the left side. So we're going to say that this is our midpoint. We're going to ask the question again. Is 6 less than, greater than, or equal to my midpoint? That is 3. Since 6 is greater than this 3, I know that my element is not somewhere over here. So what we're going to do is, once again, lower our search area. We're going to break the array in half. What I'm actually going to do is move up this index. Right? Notice that it flipped onto the other side of mid. Now what I want to do is find the midpoint. Again, we actually have two options. Because we favored the left last time, our algorithm would always favor the left. So we're going to choose this as our midpoint. And we're going to ask the question, is 6 less than, greater than, or equal to my element at mid? In this case, because it's equal, we found it. And we will return the current index, which would be index 2. So let's get a couple of more examples in, and then we will actually code this thing. All right, I have the same array pulled up here. And so I'm going to create a beginning, and we'll have an end. Okay, and so let's search for something, right? Let's perform a binary search on something other than 6. Let's go to maybe the high side this time. So maybe I want to look for 42. Keep in mind that I'm going to perform this in just a moment, where we look for an element that's not in the array at all. So the first thing I want to do is find my midpoint. Okay, I have an odd number of elements. Our midpoint is going to clearly be the one in the middle here. So we're going to have a midpoint right about there. I'm going to ask the question, is the number I'm looking for, 42, less than, greater than, or equal to? 42 is greater than, and so I can ignore the lower half of my array by simply moving up my beginning point. We'll put it just to the right of my midpoint, that is mid plus 1. So now I'm going to be able to search through this area. We're going to find the midpoint. Okay, again, because there's an even number of elements, we can arbitrarily choose the left or the right. Notice that if we just happen to choose the right, we would end up finding it in only 2 iterations. But you don't know that in advance, right? If I was looking for 23, I'd be upset in this case. So we'll arbitrarily choose the mid. We're going to ask the question, is 42, the number I'm looking for, less than, which puts it over here, greater than, or equal to the element at my current mid? Because 42 is greater than 23, I'm going to lower my search area by bringing up B, my beginning. Okay. We're going to perform another iteration where I need to find my midpoint. Again, I have two options. Because I favored the left-hand side on that previous iteration, I will always favor the left-hand side, which means that our midpoint is right here along with bag B. I'm going to ask the question, is 42 less than, greater than, or equal to? And because it is equal to, we will return the current index, which is our mid. Okay. So notice that in both of the cases that we just had, we performed 3 iterations, right? I'm talking about the visual that I did here, as well as the visual I did here. That's 3 iterations. Let's try looking for an element that's not even in the array. I don't know, something like 20. We would start out, we would have our beginning and end marked, right? We want to indicate the area that we are searching through. First thing I want to do is find my midpoint. I'm going to ask, is 20 less than, greater than, or equal to 14? In this case, 20 is greater than. So I need to limit my search area by moving up my bag marker. We're going to flip it on the other side of our mid. I now have this area to search through. What I want to do is find my midpoint. Let's say we arbitrarily choose the right side this time. Again, however you code your algorithm, it would pick one of those and then kind of stick with it, and the difference doesn't matter. There are some times where you would find it in an iteration sooner, but that's just lucking out, right? There's all the other iterations, excuse me. There's all these other iterations where maybe you wouldn't be so lucky. So it's a wash. Here is our midpoint. We're going to ask, is 20 less than, greater than, or equal to? Because 20 is less than, we need to lower our search area. And the way I'm going to do that is by moving down my end to the left-hand side of my midpoint, or simply put, mid minus 1. I now have this area, or this array section to search through. I'm going to find my midpoint. Because I arbitrarily chose the right element just on the previous iteration, our algorithm would always choose the right element, which means that out of these 2 possibilities, we would choose this element. We're going to ask the question, is 20 less than, greater than, or equal to? Because it is less than, what I'm going to do is lower my search area by making the moving end down. It's going to be mid minus 1, which puts it here. Okay. At this point, we will perform one more iteration where we're going to find our midpoint. There's only one possible element. It's going to be this 15. We're going to ask the question, is 20 less than, greater than, or equal to? Because 20 is greater than, I'm going to move up my bag by flipping it to the other side of mid, which puts us there. Okay. This is actually the point I would stop. The reason being, my end and my bag are on the wrong sides of each other, right? They've flopped sides over time. And this is ultimately how I know the element that I'm searching for is not there. Super important. This is going to be ultimately the stopping condition of our loop. Let's get started on some code. I'm in IntelliJ. I want to make a new project by going to File, New Project. I'm going to navigate to my Principles folder. And I'm going to create a subfolder called Searcher. In theory, we would have plugged in linear search here, but as we saw in our previous video, we've already done linear search. We've done like 3 different versions of linear search. I'm going to right click on the SRC, make a new Java class called Searcher. And we're going to plug in a method here, a method header. Write a method binary search that returns the index at which the specified int occurs in the specified int array, -1 if the specified int does not occur. So the name of my method is binary search. It is going in the searcher class. We're taking in an integer array, and we have an integer that we're looking for. Ultimately, we're also returning an integer. Now, I don't want you to get too confused. This is an index, right? Indices are always going to be integers. They're always going to be whole numbers because we're talking about a location in the array. This particular array, we're working with an integer array. So the element that I could potentially be looking for is an integer. If this was a double array, we'd be looking for a double. However, the index would still be an integer. Ultimately, this method is static, and I can tell because it is underlined. So I'm going to plug in a header here. Public static, we're returning an integer. The name of our method is binary search, and we're going to take in an integer array. I'm going to call that elements. I don't necessarily care what you call it, but we're going to take in an integer that we're looking for. Let's call that x or target or something like that. This is definitely a method that we want to document. This returns the index at which x occurs in elements. -1 if elements does not contain x. And I know that sounds like we're breaking in a contains method. We'll know. We'll know because our indices will flip. Okay, so the first thing I'm going to need here are some indice trackers, right? In our visual, that was beg and end, right? So I'm going to create beg, and let's back this up. Tell me, looking at this visual, where should beg be initialized to? What should the value of beg be? It's an index. It's the first element, so we're talking about index 0 here. Okay, what about end? Well, in theory, if this is 0, this had 9 elements. This is a 9, right? Well, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 elements, so this is index 9, right? No, right? Because index 0, we're going to be offset by 1. This is index 8. Simply put, you want to do that dynamically based on elements. So end is going to be just 1 less than our length. In our example, this array has a length of 9. This index, the last element, is just 1 less than the length. Okay, so I'm doing it dynamically. The first element is always 0. The last one, maybe not quite so much. I'm going to start looping. And I feel like I've already given away the condition with this example. We're going to keep looping as long as beg is on the correct side of end, meaning while beg is less than or equal to end. I want you to note that we did have an iteration, right? The very last iteration, or one before the last iteration, where we did this. Beg and end actually lined up. And that's okay, right? We still needed to check it because there was actually a possibility that this was the number that I was looking for. If we were looking for 15, we would enter this scenario where beg, end, and mid are all referencing the same index, and it is the one that I'm looking for. So we do need to perform an iteration on that. I say all that to say this should be less than or equal to. We will keep looping as long as beg is less than or equal to end. If they're ever on the wrong sides of each other, that's how we know. We've done too many iterations, we've gone too far. The element that we're looking for is not there. Okay, so while this is true, I need to find my midpoint. Okay, I'm going to create mid. In this example, it's this spot right here, right? So how do I get that mathematically? It's the one in the center. Okay, I think a lot of students would just say, oh, well, you just do length divided by 2. This thing has a length of 9, right? If I do elements.length divided by 2, that should be the midpoint. Ta-da, super easy, okay? Except, right, this has a length of 9 in this example. If we were to divide it by 2, integer truncation is going to kick in, right? We should get 4.5, but with the integer truncation, it's just simply 4. This is 0, 1, 2, 3, 4. So this looks correct. That would get us the correct index on the first iteration. That would get us the correct midpoint on the first iteration. But I don't want to base this on length because then we're talking about the whole array. I want to base it on these markers, beg and end, because as we saw in our visual, those things kind of approach each other. Whenever we're cutting the array in half, these things are getting smaller and smaller. So reference this based on beg and end. Now, beg initially has a value of 0. So another thought is that we just use a hard-coded 0. We would get the correct answer again on the very first iteration. But beg, keep in mind, can update. There were several occasions where we moved it up. So we literally need to incorporate it, and we literally need to make it based on beg and end. So think for a moment. What's a formula? Using both beg and end. Beg has a value of 0 in this example. End has a value of 8, where we can end up with the value that we want here at the mid, which is 4. Simply put, our midpoint is going to be beg plus end divided by 2. Now, you're going to be careful here. Order of operations would kick in, and it would try to do this first. That's a problem, so we want to force precedence by putting parentheses around this. So I'm going to add these two things together, then divide by 2. On the very first iteration, let's see how we get our correct value of 4. Right? We want this midpoint. Beg has a value of 0. So we're talking 0 plus end has a value of 8. Then we divide that by 2. Of course, 0 plus 8 is going to be 8. Divided by 2 gives us our value of 4. Okay. What would happen if we had like an even number of elements, right? So let's go through a couple of these iterations, and let's say that we're now at this point. Beg still has a value of 0. End has moved down. It's 0, 1, 2, 3. Okay, so we're doing 0 plus 3. I'm still going to divide that by 2, right? I am translating this formula by plugging in hard-coded numbers. Well, our 0 plus 3 is 3. I have 3 divided by 2, which in theory is 1.5. But again, we're going to have integer truncation occur. And I end up with 1. We got 0, 1. Right? Remember how we had the possibility of choosing either two places? Well, what would end up happening is because of this integer truncation, our algorithm using this formula is going to choose the left-hand side. And it's going to do that basically every time. Okay. So the first thing we're going to do is find our midpoint, which, by the way, note that because we're basing it on beg and end, let's consider this scenario where beg has changed. We saw several examples where beg was 0 and you don't see much of a difference. But let's say that beg moved up. We now have a value of 2 for beg. So this becomes 2 plus the current value of end, 0, 1, 2, 3, divided by 2. 2 plus 3 gives me 5. We divide that by 2. That is a 2.5. Because of integer truncation, this would truncate to just simply 2, meaning this index. And like I said, just because we favored the left-hand side in the previous iteration, we're always going to favor the left-hand side, and that's due to that integer truncation, and you see that we have selected this one. Now, I told you that you can kind of arbitrarily favor the left or right-hand side. The actual difference kind of comes from setting end to initially just your length. This would throw things off just by a little bit because our end marker, instead of being hovering above this last element, it would be slightly out of bounds here initially. And that's okay. And it's just going to cause us to favor the right-hand side going forward. Ultimately, the algorithm is the same. I'm going to stick with this -1 here because that's what our visuals have been doing. So we have found the midpoint. Right? We're at this step. what I want to do now is make my comparisons. I want to know, is the element I'm looking for? In our example, that's an X. Is the element that I'm looking for less than, greater than, or equal to? So we're going to have a logic branch here. We got some decisions. I'm going to throw in an if statement. If the element I'm looking for is less than the current element, okay? So X is an element. Beg, int, and mid are all indices. What I want to know is the element I'm looking for less than the element, I'll let you know how that happened, the element at my current midpoint? If so, I need to lower my parameters, right? I need to lower my search area. And the way that we're going to do that, right? If the element I'm looking for is less than, that means it's on this left-hand side. And so I want to lower my search area by bringing int down. And the way that we accomplish that is flipping it. Notice that it doesn't become mid. I don't want it to become mid because that number has basically already been crossed off the list. I want it to be one less than mid. So if this is the case, we just simply update our mid. Right? We would say that, we update our end. We would say that end would become one less than mid. That's what we accomplished here. Okay, so now we're kind of in this state where we would do another iteration. We'd find the midpoint. We'd want to know, is the element that we're looking for 6, less than, greater than, or equal to? And notice that it's greater than. So I need to add to this logic tree. I'm going to use an else if here because it's more efficient. What do I mean? Well, only one of these options can possibly be true. We're going to check for less than, greater than, or equal to. Only one is possibly true. If I just do an independent if statement, even if this was true, we would still check this, which leads to inefficiencies. It would still work, but it's not as efficient. So if the element I'm looking for is actually greater than elements at mid, and we can actually see this visually here. I'm looking for a 6. My current element is a 3. 6 is greater than 3, so I want to lower my search area. I want to cut the array in half, and I'm going to do that by bringing up bag. I'm going to flip it to the other side of mid. Simply put, it's going to become mid plus 1. So if this is the case, we're going to move up bag. It's going to be mid plus 1. My only other scenario is that the element that I'm looking for is right here. Right? If we manage to hit this, what it means is that X is equal to elements at mid. If that is true, we have found it. I want to piece out of this method. I want to return the current index. The current index being, right? In this case, we found 6 right here. The current index is my mid. Notice that I, in theory, could base it off beg, but we actually saw an example previously where end had the same value as mid. Mid is always the answer. Mid is the one that we're actually checking. So if this is true, if I manage to hit this else, what it means is the element at mid is the one I'm looking for. So we found it. We're going to signify it by actually returning the index at which it occurs. That's the current index, right? We'll keep doing this. And if I never find it, eventually beg is going to be on the wrong side of end. That means I did not find it, and I'm going to return, as our method is suggesting, a -1. Let's try this out. I'm going to plug in a main method with PSVM. I'm going to create an array. I'm actually going to grab this one. And I'm going to create an integer array. I'm going to call it something other than elements, but you can call it elements. How about nums? And I'm going to use curly braces to turn this into an initializer list. Okay, you can plug in whatever numbers you want if you're following along. Just make sure they are in order, right? Notice this is in ascending order. So now what I want to do is perform my binary search. I'm going to look through nums, and let's say we're looking for 10. This is going to give me back an integer index. In order to see it, I'm going to do an S out. Okay, what we should get, 0, 1, 2, is index 3 if our binary search is working. I'm going to right click in free space and tell my program to run. And you see we do in fact get a 3. What about like 42? Index 7, does that sound right? 0, 1, 2, 3, 4, 5, 6, 7. That's correct. What about a number that just like doesn't exist, like 99? And I get a -1 because it is not there. So that's binary search. Let's talk a little bit about the time efficiency and why you would even want to learn this thing. Just how efficient is binary search? Well, in the best case scenario, only one comparison is needed. We didn't even talk about the best case scenario. Given our array here, best case scenario is the first element we check happens to be the one that we're looking for. In our case, that's 14. Let's see it. Let's see how this would happen, right? Let's say that we're looking for 14 in this array. The first thing we're going to do is figure out our beg and our end. I now want to find my midpoint. It is going to be beg plus end divided by 2 will end up right here. I'm now going to ask the question, is 14 less than, greater than, or equal to? Equal to. I found it. I made one comparison. Keep in mind, we talked about this with linear search. That's what we care about whenever we're talking about the asymptotic runtimes, right? Number of comparisons is a really good measure of algorithm efficiency because it doesn't care about hardware. It doesn't care about software. Okay. So our best case scenario is we make one comparison. So you would say like, linear or constant. So this occurs when the element we are searching for occurs at the midpoint. This is the same as with linear search. What do I mean? With linear search, we made one comparison in the best case. So in best case scenarios, this is the same, okay? If the current element is not the one we're looking for, the array is cut in half, drastically reducing the number of elements that need to be searched through. This cutting in half contributes to log 2 of n comparisons. So binary search makes one comparison every time we cut in half, meaning that we simply do log 2 of n comparisons, where n is the number of elements. Okay, our example array here has a length of 9. So I'm just going to pull up a Google window real fast, a Chrome tab here, and do some quick math, right? I'm going to do log 2 of what? 9 was our element here. And we see 3.169. Okay. So we are going to take this number and do the ceiling, right? Truncation is effectively the floor where we get rid of this stuff. The ceiling is where you always round up, right? I can't have 0.169 of a comparison. But if we drop it down, that's just not correct. We end up always taking the ceiling that is always rounding up. So this number will round up to 4. So we are going to make 4 comparisons in the worst case. All right. Now, what exactly is the worst case? Well, it varies depending on the slight little differences, right? If I give you an array and I give you the actual code, you actually should be able to tell me what the worst case is. Right? We had some worst case scenarios where we performed like 4 comparisons. I actually believe the only worst case we had is when we were looking for 20. So one worst case scenario is that the number that you're looking for isn't even in the array. But likewise, whenever we were searching for 20, you saw that we had a final scenario where like our end, our beginning, and our midpoint all landed here. And when that happened, this was a worst case scenario. It took us 4 iterations, 4 comparisons to actually get to this point. So a number that's not in the array is a worst case scenario, but also 15 would have been a worst case scenario. Now, this is so incredibly minuscule because think about this. We're talking worst case scenario based on the number of elements is only log 2 of n, right? Given this exact same array, what would be worst case scenario for linear search? How many comparisons would you make? We just talked about how in the worst case scenario, you made 4 comparisons with binary search. But what if it was linear search? Well, a worst case scenario is if I was looking for 66. If this was linear search, I would have to go through the entire array. I would make n comparisons, linear comparisons, right? I would make 9 comparisons before I would find 66. Likewise, if I was looking for 20, I would have to check every element in order, and I would make 9 comparisons. So this log 2 of n is really good. But where it gets like mind-bogglingly insane amazing is as this thing grows, right? That's log 2 of 9, 4 comparisons. What about like log 2 of 100? That's 6.64, which again, we would take the ceiling, meaning we would round up to 7. In the worst case scenario, binary search would make 7 comparisons to find an element of 100 elements. Linear search, because there's 100 elements, would make 100 comparisons. And it just gets, worse and worse from there. With 1,000 elements, binary search would make 10 comparisons. Linear search, 1,000. So this is stupid efficient. Binary search is incredible. This means that binary search is a log n algorithm. Now, for some reason, the big O notation omits the subscript whenever it gets listed. I don't know why. I just don't know why. But this is log 2, not log 10, which means it is more efficient than the worst case scenario of linear search. So they're the same in best case scenario, but who cares about best case scenario, especially when you're talking about 1,000 elements, right? How often is the first element how often is it that the element that you're looking for just happens to be when you make the first comparison? Okay, now what about all the other scenarios? Say you're looking for an element that's not even in the array. While binary search is extremely efficient, there is a cost, right? There was a big precondition at the beginning of all this. It has to be sorted. Okay. So as it turns out, I gave some insight to sorting algorithms. Our best sorting algorithm, our best worst case sorting algorithm, maybe I should say, operates in n log n, meaning it has to make this number of comparisons in order to get the array sorted. So what this kind of means is if you were given an unsorted list and you wanted to do binary search, well, first you would have to sort it, meaning you would do this amount of comparisons. You would then have to search on top of that, which means you would do this number of comparisons, at which point you are not as efficient as linear search. Okay, because linear search is just in comparisons. Now, that being said, what we can do is just always keep our arrays sorted. Right? Having to put an unsorted array in order before performing binary search would make it worse than linear search. So linear search still has its uses. That being said, if we just keep the array in order, that's not always a guarantee, but if you have this luxury of just always keeping your array in order, you could use binary search and it's super efficient. What's interesting is binary search can actually be used to keep your array in order. What do I mean? I'm calling it binary insertion, which is we basically take binary search and we look for an element. And as it turns out, if it's not there, the last index that we were at was where it should be. Okay, so let's say that we want to insert 30 into our array. You can clearly see 30 is not there. We're going to basically figure out our beginning and our end. We'd find our midpoint. We would ask, is 30 less than, greater than, or equal to? Because it is greater than, we would basically ignore this bottom half, right? We'd move up, beg, and flip on the other side of n, meaning we would be looking at this section of the array. We would find our midpoint again. We would arbitrarily choose left or right, as we saw our algorithm tend to figure, or find the left. In this case, apparently I said the right. And we'd ask the question again, is 30 less than, greater than, or equal to our midpoint? Because it is less than, I would lower my search area again. We would get rid of these elements by chopping the array in half. All we're actually doing is moving down an index. We'd find our midpoint again. Let's say it's here. I would ask, is 30 less than, greater than, or equal to? It's less than, so I would lower my midpoint. I would lower my end. It would hop down to here. We would actually perform another iteration on the 15 and insert it there. Anyway, so what is interesting about binary search, I need to update this. What is interesting about binary search is the last index that you were on when searching for an element that's not there is actually where it should go. And it's easy to achieve that with our current algorithm by basically, right, if we hit this point, that means we've encountered an element that is not in the array. So what if I could return something other than -1? What if I could return effectively the last value of mid? Now, I don't want it to be a positive mid value because that indicates that we found it. But what we can do in practice is just simply do a negative of our mid. Now this is going to give me an error because our mid is basically declared inside of our loop. I can broaden the scope of this by declaring it before the loop. Now the current issue is it gets declared, initialized one time, and then stays the same as I'm looping. So what I need to do is basically update it with each iteration. Right? I want mid to be the latest and greatest value. We could do something like this. I kind of recommend just declaring mid and giving it a value, although that makes our thing angry. So maybe we just leave it in place. So take a look at this logic. We're still marking our beginning and our end. We're going to find our midpoint. I declared it outside the loop so we can still have access after the loop. The first thing I'm going to do in the loop is update it. Now, on the first iteration, that looks really dumb, right? We can just put a dummy value here. I wouldn't. This isn't that inefficient, but we're going to update it to the latest and greatest. And then we do our normal checks. Now, because I've broadened the scope and because we're updating our mid, if we manage to go through the entire array, we never find it, the last value of mid is where it should go. And I'll demonstrate this because let's say that we want to insert 99. I'm going to run it. Remember before we got a -1. Now I'm getting a -8, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Effectively, this is where I should put 99. Now, we should actually put it one after, but that's actually kind of cool. If I want to find 7, I'm going to binary search 7. It's going to do its thing where we do beginning, end, find midpoints, and I never actually find it. So I get a -3. So 0, 1, 2, 3. Effectively, it should go here, right? We should put the 7 here and push everything else. So that's kind of cool. If you're building your array from nothing and you use binary search to insert the elements, you can very efficiently keep the array sorted. You can very efficiently keep it in order so that you can just use binary search at any moment. I am using a negative number because it is indicating that 7 is not in the array, but if it were there, it should be at index 3. That is binary search. I'm going to leave this on the screen, and I'll see you in the next one.